Hello, I'm the monstrous Mr. Daycock, and today I am going to be giving you a formal proof of the chain rule. Now, what is the chain rule? The chain rule tells us that if we have dy by dx, that is equal to dy by du multiplied by du by dx. And I justified this last time by cancelling out the du's, treating them like fractions, and look, it kind of makes sense. But that isn't formal. That's not mathematically justified because derivatives are not fractions. What derivatives are a specific limit function. So let's consider it in terms of that. So imagine we have some function y, which is a function of something u, which is itself a function of x. That there is just a function. I could call y of yu equal to f, y of u equal to f, and then that's just a function of x. So that's all fine. And equally, this is just the same as writing f of g of x, but with f equal to y and g equal to u. And there's nothing different to that. I'm just using the variables y and u for the functions this time rather than f and g, because that will allow us to see what's going on in terms of the derivatives. So what's the derivative of y with respect to x? Well, we'll think of dy by dx is equal to our limit as h tends to 0 of y of u of x plus h minus y of u of x. And remember, we're differentiating with respect to x here, so it's the x that requires the plus h. And that's all over h. Now, I'm going to make a substitution here, one that's going to make things change up this limit a bit, but ultimately will give us a helpful insight in how the way this works. So the substitution I'm going to make is I'm going to say x plus h needs to be equal to x1. And therefore also h is going to be equal to x1 minus x. And this is just saying, look, this is our change in x. Well, this is also our change in x. And this bit at the top here is just saying that my x plus h is just some x that's a little bit further along than the original x. So I'm thinking of it as two explicit different points this time rather than as a very small change. But that means, what does that mean? Well, if h tends to 0, that means that x1 minus x tends to 0, which means we're looking at x1 tending to x. So we want to change that limit to x1 tending to x. So let's rewrite this out now. This is now the limit with the substitution of, as x1 tends to x, of y of u of x1 minus y of u of x all over x1 minus x. And that there is just exactly the same thing. This is just another way of writing a derivative. And there's nothing wrong with that whatsoever. It's just thinking of it in terms of change in y over change in x rather than necessarily the terms in terms of h. Now, what I'm going to do to justify this chain rule is I'm going to multiply the fraction, just the fraction inside, as we're kind of ignoring the limit at this point, multiplying the fraction inside by, let's not use rainbow at the moment, multiply top and bottom of that fraction by u of x1 minus u of x over u of x1 minus u of x. And now, let's see what happens. Well, we're going to get the limit as x1 tends to x of y of u x1 minus y of u of x all over x1 minus x, and then all multiplied by this extra bit on the end. And now I'm going to slightly rearrange this. I'm going to think of these fractions as together, because that's how fractions work, and there's nothing wrong with that. In this case, we're going to need some brackets here just to make sure it's clear that we're multiplying the whole thing on each side by each other. But all I'm going to do is I'm just going to rearrange the terms because we're dealing with multiplication here, so there's nothing wrong with just rearranging the terms. So this is the limit as x1 tends to x of y of u of x1 minus y of u of x all over u of x1 minus u of x, and we're multiplying each of these by, well, whatever's left in this case. Well, in this case, it's going to be u of x1 minus u of x all over just the x1 minus the x. And then remembering our brackets so that the multiplication makes sense. Now we're very, very close to our answer. Some of you might be seeing it now already. There is just one slight different thing we need to think of. Our x1 is sort of our number we're dealing with, but x is a variable, which means, and this is important, that u of x1 is just some constant, and we'll call that u1. Whereas u of x is a variable, and we can just think of that as u at this point, or at least in some cases. So I'm going to replace u of x1 with u1 where I need to, and again, remember that's just going to be a number. x1 is just a number, therefore u of x1 is just going to give us a different number. So I'm going to use this substitution in places where it's useful. So we're going to get the limit as x1 tends to x of y of, in this case I'm just going to call it u1, minus y of u, and again I'm actually just going to call this u at this point rather than u of x, all over, and here I'm going to give it u1, and here I'm going to just call it u. And we're going to be multiplying by a second fraction, and now I'm splitting the fraction into just two fractions. Here I am going to keep it as u of x1 minus u of x, all over x1 minus x. And now and we're assuming continuity of these functions, we're assuming all these functions are nice and differentiable, because otherwise the idea of differentiating them is itself questionable. So that is an assumption that exists here, so there's nothing wrong with what we've done. And because these functions are all nice in that sense, we can split this limit. So this is the same as the limit as x1 tends to x of y of u1 minus y of u all over u1 minus u multiplied by the limit as x1 tends to x of u of x1 minus u of x all over x1 minus x. Now, this one here is just really, really nice. This one is already in the form of a derivative, just remembering our original substitution of h equal to x1 minus x. And so this one, the one in green, is already just du by dx. So that's great. Over here, though, we can't quite do that because the variable inside the limit is u1 and u, but our limit is x1 tends to x. But remembering that u1 is equal to u of x1. And so, and u is equal to u of x. And so as x1 tends to x, well, it's going to have to be the case that u1 tends to u, because if I were to just think of the substitution here, that x1, as that tends to x, the u1 just tends to u. And again, this is one of the key areas where that requirement of continuity and differentiability is important, because if these functions weren't simple, if they weren't easily continuous, it might not be the case that this holds. But because of that continuity we're assuming, that is fine. Hence, I can rewrite this one, the blue one, as the limit as u1 tends to u of all of that. And given I'm going to write it in terms of that, that gives us that it is dy by du, because obviously here the derivative is with respect to u. And therefore, just as required, dy by dx is equal to dy by du multiplied by du by dx. And there we go. That is your formal proof of the chain rule. Thanks for watching, and I'll see you in the next video.